Hello and welcome back to the second video in this series on nuclear science. In this video we're going to be looking at what radioactivity is, how it occurs and how it was first discovered.
We're going to start off by defining what radioactivity actually is. Now, just because something glows in the dark does not mean to say it's radioactive, nor because something is radioactive means it glows in the dark. That's something I want to clear up straight away because it's a common urban myth. Radioactivity is formally defined as the spontaneous disintegration of unstable atomic nuclei. So that means if we have an unstable atom, it will decay radioactively until it becomes something more stable, normally by spitting out radiation. Radiation is something we're going to talk about much more in further videos. It's an entirely random process, which means we can't predict which atomic nucleus will decay next in a radioactive sample. It's also unaffected by physical conditions such as temperature, so no matter how much we heat it up or cool it down, the rate of radioactive decay will remain constant. It's also unaffected by chemical conditions, so if you have a radioactive element bonded to another atom, it won't make any difference. Other words we're going to come across that we need to define include radiation. So radiation is anything that travels outward from its source but can't be identified as matter. For example, infrared radiation, visible light, or ultraviolet light. Mainly though, we're going to talk about alpha, beta and gamma radiation, which are going to be covered entirely in the next video. A radioisotope is simply an isotope of an element that is radioactive. So if you take carbon, carbon-12 has 6 protons and 6 neutrons. That is not radioactive. Carbon-14, on the other hand, is radioactive. Those 2 extra neutrons cause nuclear instability, so it would prefer to decay into something more stable. Background radiation is the spontaneous disintegration of naturally occurring radioisotopes. So if you leave a Geiger counter on your windowsill, you'll hear it ticking away occasionally as it picks up radiation coming from radioisotopes in the soil or the Earth's crust, or that come in from outer space. The half-life of an element is defined as the time taken for half the atoms in a radioactive sample to undergo radioactive decay. Basically, this means if I have 10 atoms and the half-life is 1 year, after a year I will have 5 atoms left. The last thing we need to talk about is activity, which we define as the rate at which an unstable nucleus decays. So high activity means it's decaying fast, normally indicating it's very unstable. Low activity means it's not decaying particularly quickly, so it's probably going to have a long half-life. We need to talk a little bit about how radioactivity was discovered. It was first discovered by this chap who's called Henri Becquerel, who was a French scientist, and he was working with uranium salts. One of the experiments he was doing was wrapping uranium salts in photographic film, which was used in the olden days to take photographs. If you exposed it to light, it would go dark. Now, he found that when he wrapped a sample of a uranium salt in this photographic film, despite the fact there was no light there, it still went dark. So he came to the conclusion that something from that uranium salt was causing this, and it turned out to be radiation. For this discovery, he won the Nobel Prize in Physics in 1903. And actually, he has a commonly used SI unit named after him. So 1 becquerel is a measure of activity, which we talked about before, and is equivalent to 1 decay per second. Continuing on from Becquerel's work were Marie and Pierre Curie, who are shown on the right. They suspected that the uranium ore pitch blende, now known as uraninite, that Becquerel was working on contained other radioactive elements than uranium. The pair won the Nobel Prize in Physics in 1903, the same time as Becquerel, and Marie won it again in 1910 for the discovery of radium and polonium. They too have a unit named after them, the Curie, which is equivalent to 3.7 times 10 to the power of 10 disintegrations per second. Since this is such a massive quantity, it's tended not to be used anymore. Don't forget to check out the next video in this series to learn more about the types of radiation associated with radioactive decay and their properties.